The last topic for this unit is inverse functions. We are going to identify and recognize inverse relations and inverse functions. We are going to use the horizontal line test. That may sound familiar to you, but it's different than the vertical line test. We are going to find the inverse of a function, and we are going to look at the relationship between the graphs of a function and its inverse. Let's start this with a little motivation for what we're really doing here. In 2020, ECC's in-district tuition rate is $132 per credit hour. With this information, you can figure out your total tuition costs for X credits using T of X equals 132X. The idea is that if you have however many credit hours you have, you multiply that by 132, and that'll tell you your total tuition. What if you knew what you paid in total tuition, but forgot how many credits you signed up for? So you knew your T, but not X. Could you figure that out? Well, you could use this equation for that, right? Whatever that T is equal to 132X, you could plug in the number for T for the tuition and then solve for X by dividing by 132. But you could also write this as a function X as a function of T, where X represents the number of credit hours, and then divide the total tuition by T. The idea here being that instead of multiplying by 132, multiplying the number of credit hours by 132, we can sort of undo that multiplication by dividing the total tuition by 132. So in that way, we see that like multiplication and division kind of undo one another, right? This gets to the idea of what inverse functions actually do. Here's another graphic for you, hopefully to help you see what the relationship between a function and its inverse do. So suppose we have f that turns an apple into a banana, then the inverse function, and we don't denote that with this notation, will turn that banana back into an apple. So the way this relates to the tuition example is to say, okay, let's suppose you start with your number of credit hours and you get your tuition, right? Credit hours to go to your tuition using this function here, this T of X. And then from there, you can go back to credit hours if you use the X of T, but which would be considered the inverse of the T. Okay, so that's how this kind of is relating. Here's the formal definition of an inverse function. The inverse function of a given function is one that undoes the action of another function. Not really the formal definition there, but just to give you an idea. The function g of x is the inverse of the function f of x if f composed with g of x is x and g composed with f of x is x. That's why we needed that composition of functions in the last topic there. This happens when the input, usually x, and the output, usually y, values have been switched. Let me give you another graphic to help you see what's going on here. Suppose f takes a to 3. That means f of a is equal to 3. And it takes b to 1. And it takes c to 2. Then the inverse function will take 3 to a. It goes the other way. So it's kind of like your f and your x and your y have been switched. Your inputs and your outputs have been switched, is the idea here. So that's what this statement is referring to here. Okay. Find the inverse of this function. Well, f inverse, so f takes 1 to 2, f inverse is going to take 2 to 1. F takes 3 to negative 1, the inverse will take -1 to 3, and the same thing on that last ordered pair there. What if you have an equation, though? This is not quite as clear how we deal with that. The idea of the x and the y being switched, though, so that we can sort of go backwards, one thing I should point out here. Let's suppose we start with 1, f takes it over to 2, and then f inverse takes it back to 1, right? So we're going to try to get that same relationship or that same action happening when we have an equation. One thing to think about here with this function that we have down here, f of x equals 5x minus 7. What that means is whatever your input value is, your x, you multiply it by 5, and then you subtract 7. Well, to undo those, multiply by 5, then subtract 7. To undo that, to get back to where you started, the opposite needs to happen in the opposite order. So it makes sense to me to add 7 and then divide by 5. Kind of seems to make sense, maybe? Let's see. Let's follow these steps and see what happens here. And then I want to go back up and revisit that definition of an inverse function. This says replace f of x with y. Then we interchange the variables. That's that idea that we did up here, where we're sort of, to get the inverse, we switch the x and the y, right? That's exactly what we're doing. Now let's solve for y. Add 7 to both sides. Now let's divide both sides by 5. And then using inverse notation, because this function was named f, we're going to say f inverse is x plus 7 over 5. Notice that matches what we talked about here as maybe a possibility to be able to do that. If you take the x, you add 7 to it, and then divide that whole thing by 5. That's the inverse function we have here. Let's go back to this definition for a second. This composition of functions is an important idea, and I wanted to wait to address it really until I was made sure we were clear in what we were talking about with the idea of getting back to where you started. This f composed with g of x, fog, f of g of x, means you put x into g, whatever you get out of that goes into f, and you get x back. I hope that that's clear, that that exactly does define what we've been talking about with this inverse function. It's the idea that you start with f, you run it through g, and you get some g of x. Now, when you run g of x through f, you get back to the x. So you're getting back to where you started. That means this f is the inverse of g, and vice versa. G is the inverse of f. They come in pairs like that. Okay? So that's the idea, or why that definition, that composition, getting you back to x, works. Let's try this one. First step is to write y equals 2 over x plus 6. Switch the variables and solve for the new y. I'm going to multiply both sides by y plus 6 here. Get rid of that denominator. Divide both sides by x. You could distribute and it will get you the same result, but I'm going to just divide by x because I'm trying to get that y by itself. So now let's subtract the 6 here. So that means G inverse. I had to look to see what the name of my original function was. Is 2 over x minus 6. That will be the inverse function. If you do the composition, let's just do a real quick check. Let's do this one just because algebraically it's a little bit faster and I just want to save a little bit of time here. Let's check f composed with f inverse here. That means in place of the x in f, we put the f inverse function. That's x plus 7 over 5. This is going to simplify to x plus 7 minus 7, which is indeed x. You should check the other way to where I see an x in f inverse, put f. So in place of this x right here, I am putting 5x minus 7. Plus 7 and then over 5. That's 5x over 5, which is x. So indeed, we do get x when we do the composition both ways. Let's do one more here. Y equals x squared plus 3. Switch the variables. X equals y squared plus 3. X minus 3 is y squared. Y equals, oh, wait a minute. I would have to do plus or minus the square root of x minus 3 for that square root property, right? Problem, I cannot use this notation for this. That doesn't work because that is not a function. For it to be a function, I would need to be able to plug in a single value, like let's say x equals 4. When I plug in x equals 4, I get plus or minus the square root of 1, which is positive or negative 1. So x equals 4 goes to y equals 1 and y equals negative 1. Not a function. So we definitely can't use that inverse function notation. Now you can talk about an inverse relationship. One thing that is sometimes done is there's a restriction put on the domain of this, and we'll talk about that in a second. Let's just a reminder, we just talked about this. Relation is a function if no x value corresponds to 2 different y values. So important fact here, not every function has an inverse that is a function. One more reminder, the vertical line test determines if a graph represents a function. Okay, if it passes the vertical line test, it is the graph. If the graph passes the vertical line test, that is a function. The horizontal line test tells us that a function has an inverse if there's no horizontal line that intersects the graph of f at more than one spot. Let's talk about this. A couple examples, and then we'll talk about why. This fails horizontal line test. That means this function does not have an inverse function. Okay, the inverse of it might be, you might have an inverse relation, but it is not an inverse function, meaning it's whatever you get as the inverse would not be a function. This one, no matter what horizontal line we draw, it passes the horizontal line test. So this function, it is a function because it passes the vertical line test, does have inverse. Let's talk about why this is true, that the horizontal line test tells us if a function has an inverse. Remember, the reason the vertical line test works is because, let me draw something that doesn't. Let's say a circle. Okay? We have here and here intersection points. That means for this one x value, we have two y values that correspond to it. That's a violation of it being a function. Now let's think about, if we're talking about the inverse switching the x's and the y's, then we can't have in the original two x's go to the same y. And down here I have two x's, three x's actually, going to the same y. You have this x value, and this x value, all corresponding to that y value. And so that doesn't work. We call a function like this one in the right picture, we call it 1-to-1, because for it to be a function, each x has to go to one y. For it to have an inverse, each y can only have one x that goes to it. So 1-to-1 means for both of those to happen, one x goes to one y. That's why we call it 1-to-1. Let's take a look at this function. This I like because it's a good opportunity to remember what this function is, thinking about our transformations of functions. Parent function, y equals x cubed. The -3 on the inside shifted right 3. Well, remember, the cubic function is this sort of snaky thing, right? So when we shift it right 3 spaces, we just get this. It passes the horizontal line test. This is a function that we would call 1-to-1 because no matter what x value you pick, you get one y value. No matter what y value you pick, there's only one x that corresponds to it. So it passes the horizontal line test. Therefore, f inverse of x exists. Okay, and is a function. I wouldn't use that notation if it wasn't. Just wanted to be clear that we are answering that question, whether it's a function. We could try and find it. Let's do it. Y equals x minus 3 cubed. Switch the variables. Y minus 3 cubed. Cube root both sides. Remember, when you cube root or any odd root, you don't need the plus or minus. And then add 3 to both sides. So f inverse of x is the cube root of x plus 3. Okay? So I'm thinking here about the steps. If you evaluated this, you would subtract 3, cube both sides. You're kind of undoing that, right? Cube root and the plus 3 undo that. So... all right, the last thing I wanted to talk about here is the graphs of a function and its inverse. These graphs, f and its inverse, will always be symmetric over the line y equals x, meaning if we folded right along here, picked up our paper and folded right along there, you can do it. You have paper in front of you. Pick it up, fold it on that line. These two should look the same. Like if you held it up to a light, they would be right on top of one another. I want to think about why that is the case. Let's think about this point here. That point is the ordered pair 1, 0 on F, right? On F inverse, hold on, let me put this down so it's clear. On F, we have 1, 0. On F inverse, that means we should have the ordered pair 0, 1. We are switching the x's and the y's, right? So to do that, you're going to flip over, you're flipping those values, you're going to flip over that x and y. This is the ordered pair 0, 1. That corresponds to 1, 0. Same thing over here. This is, I don't know, 3, I'm going to guess here, approximately 3, I don't know, 1.6-ish. Making a guess here. That means the point 1.63 should be on this graph here. Okay, so that's what's happening there in the graphs of those. That wraps up Unit 2. Be sure to ask if you have any questions. I am here to help. We covered a lot in this unit, and a lot of it all about functions is going to lead us into our future units. So it's important that we have a good firm foundation here so that as we build and grow on these things, that we can feel confident in these base foundations.